Solve the system of nonlinear equations using the elimination method. Then graph the system to understand the solutions. Since we have an x squared term in both equations, we can eliminate the x's. Notice we would not be able to eliminate the y variable because in the elimination method, we can only multiply an equation by a non-zero constant. We cannot multiply by y because that would change the graph of this second equation. So the only variable that we can eliminate is the x, and we can do that by multiplying the second equation by -1. Let's notice that we didn't do anything to the first equation, so let's just copy-paste that down, and we'll distribute this -1 into the second equation so we get -x squared plus y is equal to +7. Now let's combine these two equations, and we see that the x squared term drops out, and we end up with y squared plus y is equal to 20. So we've merged these two criteria now into one equation with only one variable, and this equation is quadratic. So we're going to set it equal to 0 to determine which of our quadratic methods we'll use to solve it. So let's subtract 20 from both sides to get y squared plus y minus 20 is equal to 0. And this does factor into y plus 5 times y minus 4 is equal to 0. So we set each of these factors equal to 0, and we get y is equal to -5 and y is equal to +4. The solution to a system of equations will be ordered pairs that are on both graphs, which means that they will be intersections between the graphs. And so we have two y values that are the y coordinates for these potential solutions. In order to determine the x coordinates, we need to take these and plug them back into the original equations and solve for x. Let's start with the first equation. So we have x squared minus plugging in -5, which is the y coordinate that we found, and determining who is the x value that causes that output to be -7. So we get x squared plus 5 is equal to -7. But when we subtract 5 from both sides, we see that we get x squared is equal to -12. And when we take the square root of a negative quantity, we get plus or minus 2i radical 3. And if it requires an imaginary number to get an output of -5, that means that this is not a graphable point, which means that there is no ordered pair on this graph with a y coordinate of -5. And that means that this could not possibly be the solution, because the ordered pair needs to be an ordered pair on both graphs. So let's see about y is equal to 4. This ordered pair needs to be on both graphs, so let's just start with one of them. We'll do the second one again to see x squared minus plugging in 4 for y is equal to -7. So we get x squared minus 4 is equal to -7, and again, we're going to get a negative number on the other side of this equation, and when we take the square root of a negative number, we get kicked into the imaginary numbers. So this is plus or minus I rad 3s, which means that this is not a graphable point either. And there is no ordered pair on this graph that has a y coordinate of +4. So neither one of these work. So it looks like we may not have any solutions to this system. But let's graph the system so that we can understand a little bit more about what's going on here. The graph of this first equation is a circle that's centered at the origin with the radius that's rad 13. And the square root of 13 is approximately equal to 3.6, so we have a circle that looks something like this. To graph the second equation, let's solve it for y. So we have x squared minus y is equal to -7. Let's subtract x squared from both sides to get -y is equal to -x squared minus 7, and then divide both sides by -1 to get that y is equal to x squared plus 7. So this second equation is a parabola that's opening up that's been shifted up 7 units. And while this graph isn't perfect, it's enough of a concept drawing to illustrate the fact that these two graphs do not intersect. So there is no solution to this system. And when we tried to find those solutions algebraically, we kept getting kicked into the imaginary numbers.